Hello, this is Wednesday's lecture for week 13. We'll be finishing up chapter 26 with a discussion of lenses. The last three sections of chapter 26, you'll notice the 26.5 is about the eye, and if we understand things about lenses, then we can understand the eye and corrective optics for the eyes and glasses and a host of medical applications, including fibroscopes and endoscopes. So let's start by looking at the different types of lenses and classifying them in terms of whether or not their rays converge or diverge. If you see this group in group A, the lenses are thicker in the center than they are on the outside. And in group B, the lenses are thinner in the middle than they are on the outside. Even though they might have this funny shape, we still characterize them by whether or not they're thicker in the middle or thinner on the outside. And I'd like to sort of demonstrate that by showing what's happening when light enters a lens and either converges or diverges depending on its relationship to the normal. So imagine that light is coming in through parallel to the axis, and let's blow this up. And our normal line remember from our study of Snell's law that the ray will bend. Looks like maybe that's a better normal line. I was saying that from our discussion of Snell's law, we remember that when light travels from a medium with a lower index of refraction to a higher index of refraction, it will bend towards the normal. So in this case, towards the normal looks like this. And then when it leaves that medium, looks like maybe the normal line is here. It's going to bend away from the normal. So straight line would be in this direction, but since it bends away from the normal, it looks like it's going more like that. It might be a coincidence, actually not, that it's parallel to the normal of the first interface. You can see that that's a consequence of the mirror equation, which we won't actually use in this class. But the important thing to notice is that the light that enters parallel to the axis is converging on the other side of the lens. And what we're going to do is we're going to skip this little fancy bit in the middle, and we're just going to make an approximation called the thin lens approximation that says really all we need to be concerned about is what's happening to the light on the other side, and that is that it's converging towards the principal axis. And the point that it converges to, that a parallel ray converges to on the principal axis, is called the focal point. So this is familiar to you from our conversation of mirrors. Now if we look what's happening with a diverging lens, if a light ray enters parallel to the axis, now our normal looks like something like this, and the light is going to bend towards the normal in this surface. So see, this would be straight ahead, this is towards the normal. Now the normal on this surface looks like maybe that. So now the ray leaving is going to bend away from the normal. So let's see, this would be straight ahead, away from the normal would be like this. So again, parallel to the normal of the first surface. And using the thin lens approximation, instead of worrying about what's going on in the center of the lens, we're just going to assume that the lens is thin enough so that it just bends once. It just bends once at the center. And this is the way we're going to draw our ray diagrams. And it's diverging away from a point on the near side of the lens. So even though there's no light actually coming from there, it looks like it's coming from a point here, which is the focal length. So a difference between lenses and mirrors is that lenses actually have two focal points, one on either side of the lens. So you'll notice the curvature on this side of the lens is matched by the curvature on this side of the lens, and so we say that there's actually a focal point on this side of the lens because the lens has two surfaces. And similarly, the focal point of a diverging lens occurs on both sides of the lens. But when we're using our lens equation, remember we have this relationship for the image distance and the object distance. This was true for a mirror, except for a spherical mirror, we used c over 2 instead of 1 over f because the focal length was half of the radius of curvature. But this is still going to work for us. We're still going to be able to use this relationship now for lenses instead of mirrors. The only pitfall really for doing these problems is correctly identifying the sign of the focal length. And the focal length for a diverging lens is negative because no light actually travels there. And the focal point for a converging lens is positive because light does actually converge to that point. So our focal length is positive for a converging lens and negative for a diverging lens. And your book has a summary here of what the ray tracing diagrams look like for converging and diverging lenses. And you'll notice there's only one picture for a diverging lens, and that is because the image is always going to be virtual and upright. And for a converging lens, the image height and inversion and whether it's real or virtual depends on how far away we are from the focal length. And I'd like to elaborate on that point a little bit more. Before I do, I wanted to mention that we have 3 rules for ray tracing. Remember the rules for ray tracing for mirrors or parallel in, focal point out, focal point in, parallel out, and we went straight through the center of curvature of the mirror. Well, this is very similar for a lens, except now instead of going through the center of curvature, we're going to go through the center of the lens, meaning the point where the lens intersects the principal axis. And when I was first starting ray tracing diagrams, I would sometimes get confused about which focal point to go to. And so I think these are my pro tips for eliminating that confusion. And one is that we have to remember from this, we always have this image in our minds, and we have to remember that for a diverging lens, that rays bend away from the principal axis, and for a converging lens, that rays bend towards the principal axis. And if you remember those 2 rules, then you won't be confused about where the light is going to with respect to the focal point. And then the other key tip is when we're doing our ray tracing diagrams, parallel and focal point out, we can only use, focal point and parallel out, we can only use each focal point once. So if you use one focal point for ray 1, then you can't use that same focal point for ray 2. So that'll also help eliminate confusion, I think. So this is from last section where we talked about the makeup mirror. So a concave mirror, and what happens in the makeup mirror when your face is outside of the radius of curvature of the mirror. The image that you see, all of these 3 pictures share this big fat green ray, but the image, in the case of the blue line, is this tiny little blue line here. So it's inverted, it's smaller, and since light is actually going there, it's real. So let me write that down. In this region of space, for d naught greater than c, I have that the image is real, inverted, and smaller. But when I'm between the center of curvature and the focal length, so now I'm looking at this line, I see that the image is still real, it's still inverted, but now it's bigger. And finally, when I move really close to the mirror, when my image is, when the object is inside of the focal length, then we look at this line and this line intersecting. We see that they don't on this side of the mirror, so we have to go backwards. We follow the arrowhead backwards to see where the light appears to be diverging from, and follow this backwards to see where the light appears to be diverging from, and they intersect here. So that means the image it's virtual, it's upright, and it's bigger. Veterans Upward Bound. Okay, so 3 different regions for a concave mirror, and we'll see it's very, you'll notice that the rays converge to a point with the concave mirror. And similarly for a concave lens, we'll see that we have 3 different regimes for a concave, for a converging lens. And 2 of them are interesting from a technological point of view. That's these 2. So let's do the first situation first, when the image is outside of, oh shoot. Okay, this is actually D naught is greater than 2F. Okay. So if we're out here someplace. Oh, by the way, if you don't have graph paper, then there's you can download this free 1/4 inch graph paper if you want. I put a copy on Cengage. Sorry, I mean on where did I put it? Here. So graph paper 1/4 inch PDF. You can download this if you want. You can use that for the homework if that helps you. If it doesn't, just use a ruler to measure out the distance between the center of the lens and the image, and then make the corresponding measurements to see where your image ends up. Okay, so in this, let's use green. And see parallel in, focal point out. Okay, let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Here's my focal point. I remember that rays will, for a converging lens, that means the rays go towards the principal axis. So I need to draw a line that's going through the focal point towards the principal axis. And then my second line is focal point in, parallel out. So you might be tempted to say, well, that means I go to the focal point, right? No, you don't go to that focal point. We've already used it, so you can't use this one. You've got to go through this focal point now. So you're going to go through that focal point, and it goes out parallel. And where these 2 rays intersect is our image. And we see that the image is real, it's inverted, and it's smaller, right? Because here 1, 2, 3, 4 is my image height, or my object height, and my image height is 3, so this is smaller. So to classify this, I would say real, inverted, smaller. Okay, now let's look what happens when the image is between the 1 focal length and 2 focal lengths. I don't know, let's try this. Make it too high. Go parallel in, focal point out. I remember I have to go towards the principal axis. 1, 2, 3, 4, 5. Here's my focal length on the other side. Oops. focal point out. I have to use this one. I can't use this focal point again, so I've got to use the second one. And looks like it's doing that. Now this one's parallel. Okay, and looks like if I had extended this line, it looks like the image would have gone here. So this object height is 2, the image height is 1, 2, 3, 4. So it looks like my image is real. It's inverted, but it's bigger. So the application for this is a projector. We've taken the object and we've enlarged it, made it bigger, and projected it someplace on the other side of the lens. So this is, I don't know if you're, well, yeah, of course you're familiar with the projectors that we use in class. So the image is close to the lens on one side, and it's very far away from the lens on the other side, and it's bigger. It's upside down, which means that if you want to project a right side up image, obviously your object has to be upside down. So that's a projector. Its purpose is to project the image away from the object. Okay, and then the last situation we want to look at is magnifier, and that's when the object is inside of the focal length. So let's go 3 away. Do 2 high again. So first line, parallel in, focal point out. Next line, focal point in, parallel out. I can't use this one, so it's going to have to be coming from there. I know that there's no light coming from the focal point. I know that the light is scattering off the top of my image, but I'm drawing this line to show that any light that would be that will go out parallel to the axis would have had to come from the focal point on the other side of the lens. And so this one is parallel out. Well, we see that no real light converges. In fact, it's diverging on this side. Let's draw a third line just to enforce that. Third line straight through the center is like that. Alright, so since the rays don't converge, I need to go backwards to see where the light appears to have been coming from. And if I trace this one backwards, I get this. If I trace this one backwards, I get that. And if I trace this one backwards, I get okay, I don't know why it's great, but anyway, all of these intersect right here. So I can see that my image is virtual because no light's actually going there. It's upright and it's bigger. So you'll notice this is exactly the same as our concave mirror. We had 3 different regions, real inverted smaller, real inverted bigger, virtual upright bigger, just like for our converging lens. So I think it's important to have these 3 images in mind when you're doing the homework problems, because it will help you figure out if your image distance and object distance and so on were correctly calculated. I think it might be useful, I'm just thinking of this now, is let's see if our image that we just drew kind of crudely with graph paper corresponds to what we would get if we actually used the lens equation. So let's try that out. Here our image distance is, or I should say object distance, is 1, 2, 3, 4, 5, 6, 7, 8. So 8 units. It could be meters, centimeters, whatever you want. And the focal length is 5. So what is the image distance? Well, 1 over 8 plus 1 over the image distance equals 1 over 5. So if I solve this for di, I get 1/5. So in my calculator, I just go 5, 1 over x, 8, 1 over x. Subtract 8, 1 over x. I get 13.33. So let's see if that's about right. 13.33 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13.3 should be right here. So pretty close, right? Our graphical picture gave us an answer that's very close to what we calculate when we use the lens equation. I think this is a very powerful tool. It's quite common to make sign errors with the focal length and the image distance, where the object, well, for compound lenses with the object distance. So ray tracing is a good tool to help us see if we are in the right order of magnitude. Alright, lastly, I'd like to look at the diverging lens. It's much easier than the converging lens. There's only one situation to worry about. It's just like the diverging lens, like looking at the outside of the Christmas tree ornament. You remember, if you look at the outside of the Christmas tree ornament, or you look at the lenses of your rear view mirror, for example, the image is always upright. It's always virtual, and the size is going to depend on how close you are to the focal length. But let's just look at one of these pictures. Let's say my image is between the focal length and twice the focal length. So parallel in, focal point out. Okay, so now the question is, focal point out, do I go towards this focal point or this focal point? Well, if I went towards this focal point, I'd be going towards the principal axis, which, if you remember our rules, pro tips for ray diagrams, diverging lens, rays bend away from the principal axis, and converging lens towards the principal axis. Well, this is a diverging lens. It means it has to bend away from the principal axis. So that means this green line that went in parallel has to bend out this way. And it has to bend out, appearing that it came from this focal length. We can't use the other focal length, obviously, because that would be bending towards the principal axis. So I probably should have used an arrowhead for that one. Okay. And then let me make this dash to indicate that no light's actually going there. Alright, and then our second ray is focal point in, parallel out. Well, I've used this focal point already, so that means I need to go through this focal point. So I would be going right there, but no light is actually going to that focal point, because focal point in, parallel out means it's going in this direction. And then our last ray was straight through the center of curvature, so straight through the center of the lens, which is here. And we can see that no light is converging, which means we have to trace these arrows backwards to see where the light appears to be diverging from. So if I trace this backwards, it goes to the focal point here. If I trace this backwards, it's here. And then if I trace this backwards, it goes. Here. And those three rays converge on one point. So that tells us that our image is virtual. upright, and in this case it's smaller, but I'll leave it as an exercise to you to see what happens when you bring the object closer to the lens surface. I'd like to finish up just by doing two examples from the text. One is we're looking at a converging lens with the focal length of 10 centimeters. So I've used the graph paper using one division is 2.5, so 1, 2.5, 5, 7. So this is 10 centimeters, and then 3 times that would be the object distance. So it says construct a ray diagram, find the image distance, and describe the image. Great. So 30 centimeters from the lens. Let's try that. Alright, first ray is parallel in, focal point out. First of all, I'd like to draw my focal point on the other side. 1, 2, 3, 4. 1, 2, 3, 4. I know that corresponds to 10 centimeters. Notice I didn't even need to draw the shape here. I'm told it's a converging lens, so I've got to remember that the rays will bend towards the principal axis when they go through the lens. And I have to go through the focal point, so we're doing that. My second ray is focal point in, parallel out. I can't use that focal point. I've got to use this one. And parallel out is something like that. So my image is here, and I would guess, just looking at this picture, that my image distance is, let's see, it's 2.5 per division, right? 2.5, 5, yeah. So 5, 7.5, 10. Is that right? No, it can't be. This is 10. This has to be 15. Okay, and it looks like the height is about 1.75, so it's a little bit, it's negative because it's inverted, and it's definitely less than 1, and I'm going to guess it's about 0.6. I don't know, it could be 0.75, I'm not sure. But anyway, we'll try 0.6, see how close we are. Construct, find the image, describe the image. Okay, well, we can describe it right now. We can say the image is real, because light actually goes there. It's inverted, and it's smaller. Now let's see what the actual image distance is. So object distance is 1/30. Image distance is what we're trying to solve for. And the focal length. Now, we're given that the focal length is 10 centimeters, but is it plus 10 or minus 10? And the answer is, for a converging lens, it's plus 10 because light actually does go to the focal point. So if I solve this for di, I get 10, 1/x, 30, 1/x, subtract 1/x, 15 centimeters for di. And remember that the magnification is equal to minus di over do. Or the height of the image divided by the height of the object. But we don't have the height of the object. I just arbitrarily took 3 units here. But we do know the image and object heights. It's minus 15 over 30. So minus 0.5. I can convince myself that that's actually 1.5, should be 1.5 units. Because this didn't go straight through F, so this should be a little higher on the axis. Okay. Order of magnitude. Alright, next the object is placed 5 centimeters from the lens, so now we're inside the focal point, and we need to construct a ray diagram, find the image, and describe the, and blah blah. Okay, so let's do that again. Go too high. My first ray is parallel to, I need to do my focal point, focal length on the other side, so let me take care of that. 1, 2, 3, 4, 1, 2, 3, 4. Alright, so now I'm ready. Parallel in, focal point out. I drew it from the focal length. Alright, my image is actually here. My object, I mean. Okay. Radio, okay. So, parallel in, focal point out. I know it's a converging lens, it means it has to go towards the principal axis. The next one is focal point in, parallel out. I can't go to this focal point because it's already taken. So I need to come from this focal point. And it goes out parallel. And the last one should be straight through the center of the lens. Looks like that. No lights converging over here, which means I need to trace my lines backwards. So taking this one backwards. And then this one backwards. Shoot, a little low. This one backwards. Yeah, well, okay. It's not always perfect. So it means my image is in here somewhere in this big fat fuzzy triangle. So I'm gonna guess it's right there. Okay, so find the image. Well, the image distance, just guessing, looks like. Let's see, 2, 5, 7.5, 10, 12. Oh, so I'm putting a negative sign in front of the image distance. I hope that you agree that's the thing to do, because your book says, oh, it's because the image is in front of the lens, so it should be negative. The way I like to think about it is, no light is actually going there. If you put an index card at the location of the image, you would not actually see the image there, because no light actually goes there. So that your image distance is negative. Okay, what else can we say? Magnification. Magnification, it's positive, and it looks like it's close enough to 2. So we'll say +2. That's just doing this graphically. Let's see what the numbers tell us. 1 over the object distance. Object distance is 5 plus 5. Image distance is what we're trying to find. And the focal length is plus 5 because it's a converging lens. No, what is it? Plus 10? It's 10, right? Yeah, 10. Okay, so you can probably do this in your head, but 10, 1 over x, 5, 1 over x, subtract 1 over x. And then the magnification is minus the image distance, so minus a minus 10 over the object distance, which is plus 2. So that's it for week 13. Thanks for your attention. If you have any questions, please call or text, and the homework is posted.